Hi, so this short video will summarize the module we've had on dynamic scheduling with support for precise state. In the previous module on dynamic scheduling, we saw how out-of-order execution can keep the pipeline well utilized to improve performance, even in the face of read-after-write dependencies. We can mask the waiting time due to read-after-write hazards. But we saw that out-of-order processing all the way into the back end of the pipeline, specifically the write-back, broke correctness. We could no longer support precise exceptions, and we had to stall the dispatch stage until branches resolved. So our goal in this module was to retain correct precise state by reusing several of the concepts we saw before, reservation stations, register renaming, but we introduced new data structures, the physical register file, the reorder buffer, and crucially, we broke up the out-of-order write-back stage into two parts, out-of-order completion, but crucially, in-order retirement. So our work culminated in the MIPS R10K microarchitecture, which used true register renaming, providing more locations than there are register names through a physical register file. For every dispatched instruction, we tracked both the new output location and the old, and at retirement, we could free the old register mapping. This design avoids extra data copying, where the wide 32-bit or 64-bit data paths are connected straight from the physical register file to the functional units and back, and in particular, this design did not move data from the registers to the reservation stations. This enabled us to limit the more complex wiring to do with control and tags to carry only a few bits required to represent tag numbers or hardware structure entry. We wrapped up the module by showing the serial rollback of the processor state when the retiring instruction was discovered to have had an exception, a page fault in our example. So we undid the effects of all of the speculative instructions that followed the retiring instruction. And while this supports a precise exception model where we can abort and restart at any given instruction, this ability to recover precise state is also crucial for control speculation so that the pipeline doesn't need to stall at dispatch when branches are discovered. We have a means to roll back. Now, popping up the stack a little higher, I want to give a sense of the context of what we've just learned. I'll do a bit of foreshadowing and looking backward. Superscalar execution, out-of-order execution, and speculative execution, these are three great tastes that taste great together. We often see them combined in modern, high-performance commercial processors. Put together, they solve several problems incrementally. So let's think back to our in-order execute pipeline, and suppose we have a CPI equal to or greater than 1. Now, is that really the best performance we can achieve? Well, we've so far seen each stage processing one instruction per cycle. We send one instruction down the pipeline at a time, but we could improve performance further by going superscalar. And we will touch on this idea much later in the course, where the goal is to issue multiple instructions per cycle, keeping several functional units busy, but also requiring that we fetch, dispatch, decode, and possibly write back more than one instruction every cycle. Now, as we inject more instructions into the pipeline, trying to improve our instruction throughput, we might find that read-after-write dependencies manifest as read-after-write hazards, requiring stalls in an in-order pipeline. But we've seen that we can deal with read-after-write hazards by letting instructions pass each other in the pipeline with out-of-order execution, say Tomasulo's algorithm. But the key with out-of-order execution is to find independent instructions that we can process out of order. So if the raw hazards are still a problem, then we build a larger instruction window. We increase the size of the reservation stations, the reorder buffer, and the physical register file. But remember that branches are not rare instructions. They can be seen as often as 1 in 5 instructions, So if we want to fill a large instruction window with tens or hundreds of instructions, we need to do a very good job with our control speculation, predicting the target and the direction of many branches in the instruction window. So putting these three ideas together, this is a nice way to take sequential code and improve performance by dynamically discovering rapid issue instruction schedules to keep instruction throughput high and therefore program latency low. But is this rosy story that I told limitless? Do these techniques scale to an infinite number of transistors? Unfortunately, not. Remember that we had some expensive operations, associative lookups in the map tables and the reservation station tag fields. These operations and others limit the size of these structures that can be implemented in a cost-effective way in terms of latency, area, and power. So we will dive into those challenges and one possible solution in the form of multiprocessing in a later module, where the idea is to exploit an even coarser level of parallelism, thread-level parallelism. But before we get to multiprocessors, in the next module, we are going to tackle caches. Why do we even need them? Assuming they exist, how will we locate data in caches, replace data, and introduce optimizations to improve cache performance to drive down the latency of our load and store instructions on average? So I will see you there.